so the first speaker is Alex from UCLA.
Okay, cool. Okay. Thanks, Guido. Cool. Thanks, everyone, for coming to my talk. Today, I'll talk about the affine natural proximal. Okay, so first of all, the outline of the talk I'll talk about what the natural gradient is, and then I'll talk about what the Weierstein natural gradient is, and then we'll talk about the affine natural proximal, and then we'll go through some numerical examples, and then we'll also talk about something called where we applied our stuff to GANs. Well, and then we'll go over the numerical results there. Okay, cool. So yeah, first of all, what's deep learning? Maybe all of you guys know, but maybe some of you don't. But it's just a framework for learning data representations. And so yeah, you can use these representations for tasks like classification or generative modeling, and more. Okay, so natural gradient. So the point of natural gradient is to have your optimization be invariant to how you describe your problem, right? So in stuff like deep learning, you have parameters. Those parameters are supposed to describe probabilities, but if those, and so you have this sort of like bridge that you need to align, right? In this example, it's sort of like this is like your parameter space, theta, and your parameter space describes a probability model. So here, the variables would be like, what's the probability of x given your parameter theta, and then here would be the actual probabilities themselves as the points. So yeah, so it's like 3 levels of abstraction. Yeah. But okay, so let's try to rethink what steepest descent is in order to motivate the natural gradient. Okay, so we have a very simple gradient descent update. So we have 2 coordinate systems, right? X and theta, and where x is maybe a inverse theta, and we want to minimize f of theta. So you can do a gradient descent in the theta coordinates, or you can do a gradient descent in the x coordinates, where you switch it. But if let's say at the kth iteration, if axk equals theta k, does axk plus 1 equal theta k plus 1? And the answer is no. If you just do the simple math, you just multiply this side by a, and axk plus 1 will then equal these expressions, and this expression here doesn't equal this one here. So definitely axk plus 1 doesn't equal theta k plus 1. So you definitely need to take care of how you parameterize things. Another example here is you have an ellipse, or just like a circle, just a bunch of circles as your level sets. So like these are level sets. There's like ellipses. These are circles. So if you do a gradient descent, it's kind of bad and if you take a large step, you're gonna oscillate a lot. Whereas here you just go straight to the center. So if you reparameterize your problem, the optimization can become much easier. Okay. So let's sort of rethink what steepest descent is then, right? So actually, if we rethink what steepest descent is, then let's say we have a metric on the input space, x, and so it's like the distance d, and we have a function f. So a natural way to define steepest descent is to actually say, like, hey, given a step size alpha, then you want to find the direction of change such that the distance between where you are currently and where you want to go next is exactly equal to alpha, and you want to take the argument of that. So it's basically like just like a ball around your current iterate, and then you want to find what point is exactly the smallest one. So that's actually steepest descent with a fixed step size. Because otherwise, if you're just doing a gradient descent in the naive way, it's sort of you're just saying, oh, what's the steepest direction in when alpha is pretty close to 0, very much close to 0, and so you might not get the steepest descent. You might oscillate a lot, like in the previous picture. So anyway, this is like the actual steepest descent in metric space. Okay, so this is the basis of the natural gradient. Okay, so let's try to think about actually steepest descent in probability distributions now. So in learning, we more or less want to find the best probability distribution that minimizes the loss function. So basically, you just change it to p for probability. But you know, a lot of the times we have parameterized models, parameterized by theta. So maybe actually what we want to do is we want to change the metric so it's the distance between p theta and p theta plus delta equaling alpha, and then the loss function will be of theta plus delta. So, okay. And so, you know, mainly when the natural gradient was first proposed, well, when people say natural gradient, they use the KL metric as the distance function on the input space. So the KL metric's like that. So basically, this is what natural gradient is. Basically, you have KL of p theta and p theta plus delta. And then what you can do is you can sort of, this is sort of like, what you can do is you can do some Taylor expansions to approximate what the delta star equals, and you'll get this expression over here, where f sub theta is the Fisher information matrix, so which is basically, you can sort of think of it as the Hessian of the KL. So basically, yeah, you just expand this in Taylor series, and then you can solve for delta star like approximately exactly. Okay, and you'll get that expression. Okay, so the natural gradient update scheme will then follow theta k plus 1 equals theta k, you know, minus h times the Fisher information matrix inverse times the gradient. Yeah. So where h is the step size. So basically, yeah, natural gradient uses the KL between probability distributions, but you know, we were thinking, well, what about the Wasserstein metric instead of the KL metric for probability distributions? So yeah, the Wasserstein metric, you know, used in stuff like optimal transport and stuff like that. Okay. Okay. Then we have something called the Wasserstein natural gradient. So Wasserstein is a little bit more continuous than KL. So some reasons to use Wasserstein is, yeah, it's more continuous than KL. For example, if we just look at these probability distributions, so what the probability distributions A and the probability distribution B. And so what's the distance between them? Well, if you compute the Wasserstein distance, the Wasserstein 2 distance, you'll get that it equals 1 minus alpha a1 minus b1 squared plus alpha a2 minus b2 squared. For the KL, unfortunately, it's just going to be infinity. It's going to be because there's no overlap. So yeah, it's just going to be infinity. So it's not really useful. And you know, for Euclidean, it is okay. A1 minus b1 squared plus a2 minus b2 squared. But the thing is, like, it doesn't account for the fact that you have a lot of the mass on the B2 and A2. Okay, so when you think about it, yeah, and then L2 also gives you infinity because you're integrating over all of R. But so anyway, when the A converges to the B, like when it gets closer, KL will just tell you, oh, it's just going to be infinity, 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 and then, you know, 0. But then for the Wasserstein, for the Euclidean, it will converge like correctly, but it weights this guy too much, these guys too much. But then for the Wasserstein, it weights these guys correctly. So it's a lot more continuous, and it makes a lot more sense. Okay. So the Wasserstein gradient, yeah, measures the distance. So this is how the Wasserstein 2 distance looks like. So yeah, it's just the infimum over all joint distributions with marginals p and q. Yeah. Okay. So then basically the Wasserstein natural gradient will just change this bottom part from KL to W2. So similar to the KL case, we can, you know, write the Lagrangian, expand by Taylor series, and we'll get an expression that's similar, where G is the sort of the metric tensor, the Riemannian metric tensor. Okay, let's go talk about the affine natural proximal. Okay, so, you know, yeah, we have learning problems, right? And we want to minimize with respect to theta of some f of theta, right? So, okay, so if we want to perform natural gradient descent, we have theta k plus 1 equals theta k minus some metric tensor inverse times the gradient of the objective. Okay, yeah, so here G of theta is the matrix representation of the natural metric structure on the probability space. So, and then, yeah, you can think of the above, you know, this is sort of like just a remark. You can think of the above as a Ford-Euler discretization of the gradient flow. Okay, but anyway. So yeah, okay, you have a probability space P omega G. And for a probability model rho theta, then you can sort of represent, you can have the matrix representation, G of theta, which is equal to this expression. So basically, you're pulling back small g into parameter space to get big G. And I just want to note that if the small g is going to be the weighted elliptic operator, then the matrix representation will look like this. Whereas if small g is 1 over rho theta, then the matrix representation will look like this for the Fisher row. Okay. Anyway, yeah. So in order to perform gradient descent, we need to compute this guy, right? But this guy, especially when theta is huge, like in deep learning where you have a billion weights, literally, then it's kind of hard to not only compute the full matrix, but also to invert that matrix. So basically, we thought of another way to do it, which is the proximal update. So basically, the proximal update looks like this. Theta k plus 1 equals proximal of this guy, where the distance will be sort of a geodesic, right? And but in order to practically calculate the distance between theta and theta k, we can use this approximation here, where we sort of just look at the endpoints. Like, yeah, we can take the integral, but instead we just look at the endpoints. And for small enough distances, the approximation is pretty good. And so we can turn this above into a variational formula to compute the distance. So now we only need to supremize over some function space now, which is pretty great because you can either, if you work on it, like sometimes you can't solve things exactly, so you just sort of turn it into an optimization problem to get an approximation, and sometimes that's good enough. And this works all the time, especially in deep learning. So anyway, yeah. So basically, you have this function class here. So the main trick here is to restrict this function class into an affine function class of this form, where you have sort of these like basis function psi and some coefficients. C, I think, yeah. OK, cool. So for the Wasserstein metric, we'll have something that looks like this. We want to supremize over this expression over where we restrict phi to be in this function class, given some basis function psi. And the same thing with the Fisher row. This is how the Fisher row would look. OK, so we have so basically, if we let the psi equal this sort of, if we choose these guys as basis functions, which is like sort of an order 1 approximation, then the Wasserstein affine natural proximal distance will look like this. The Fisher row will look something like this. As you can see, the Wasserstein distance is a lot more simple than the Fisher row. But if we can also go above, we also went one step ahead, one step above, and got an order 2 approximation. So it's basically just restricting everything to the quadratic functions. So phi, you just choose phi as the quadratic functions. And you'll get that the Wasserstein distance looks like this. And the Fisher row approximation will look like this. OK, some numerical examples. So yeah, as you can see, when we do this stuff, it works pretty well. On the left, we have a maximum likelihood estimation of an independence model. And on the right, we have this is like a classification using a CNN, a convolutional neural network. And we can see that the order 1, order 2 Wasserstein proximals, their optimization curves are much better than just the standard SGD. Okay. And so this is sort of the algorithm if you want to look it up. This is mainly for the video. If you want to rewatch the video and look at the algorithm, you just pause the video. OK, Wasserstein proximal of GANs. We also applied some of these ideas to the Wasserstein to GANs. So what is a GAN? A GAN is just a generative adversarial network. Basically, you have something called a generator and a discriminator. The discriminator sort of measures the distance between your generated samples and real samples. And at the end of the day, what you want is the generator, because you want to generate samples that look indistinguishable from your real examples. OK, what can GANs do? GANs can create new celebrities, new celebrity faces. So these are not real people. I'm pretty sure you've also seen stuff like deep fakes. That's used by GANs, generative modeling. GANs can also do stuff like image-to-image translation. So maybe, you can change summer time into a picture into a winter picture, stuff like that. Maybe you've seen the apps where you can take a picture and it can render the picture as if Van Gogh drew it, stuff like that. OK, so some standard performance functions for GANs just look like this, where you're just minimizing the log likelihood of real images and the log likelihood of fake images. Yeah. So I don't know. Yeah. Anyway, so basically, you have some performance function. OK, so you can approximate the Wasserstein distance of with a discriminator, and then move the constraints in the objective to arrive at this guy. So which we call this the Wasserstein proximal. And this, very much looks like the proximal update here. OK, some numerical results. Yeah, this is just applying ideas of the affine natural proximal. Just one last thing. Something called the Frechet inception distance. Not really important, but it's just a way to evaluate the quality of your generated samples. OK. So yeah, Wasserstein natural. This is just the algorithm that maybe you want to pause the video and look up later. Let's go straight to the numerical results because I'm not sure about the time. But OK, so yeah, some results with Wasserstein proximal. So basically, this was trying to generate samples using examples from a image database called CIFAR10. And so as you can see, this is like, so this axis is the quality of your generated samples. The lower the better. And this is like the wall clock time. So as you can see, when you use our methods, it's much better. Similar story here. This time we use a difference performance function to try to see, we use a difference performance function and try to regularization here. And then similarly on another performance function, as you can see, it always does, pretty well. Yeah. OK, and then another one. This is a different data set, Celeb A, which is celebrity faces now. We're trying to generate new celebrity faces. OK, and then we also wanted to test the stability of our algorithm. As you can see, when you just use a standard GAN training, it goes it wildly oscillates. Whereas if you apply a regularization, it's more stable. So practically what this means is, let's say you're training, and at some time you want to say OK, let's stop training now and let's just save the generator. Well, you might get a generator that's horrible, right? Whereas with ours, it's pretty safe in terms of the save point of when you want to save your model. So, and then we also tested stuff with higher learning rates, and we also see that ours is a lot more stable. As you can see, just with standard training, it sort of destabilizes. But with our regularization, the performance is much faster and more stable. Or more stable, yeah. And this is just something called a latent spacewalk, which is if you want to test if you're over memorizing the data set, then what you'll see is these images would not look as smooth of a transition as they look right here. So basically, our regularization says that it doesn't over memorize. So yeah, cool. All right, thank you.
So we have a couple of minutes for questions.
So how can you quantify the difference between the Wasserstein Proximal and true Wasserstein Steepest Descent?
Sorry, what though?
So you have the Proximal procedure which approximates the steepest descent using the Wasserstein distance.
Yeah.
Can you quantify the distance between this and the true steepest descent?
You mean true steepest descent as in terms of
in terms of, you have a ball in the Wasserstein space.
Yeah. Oh, yeah, I mean, basically we just do an approximation to the Wasserstein metric. So, in terms of an exact distance, it's kind of hard to say what the exact sort of distance is, but we just ran our numerical examples and it worked pretty well in terms of the approximation. Yeah.
But Wasserstein metric depend on the metric on the base, right?
Yes.
Yeah.
In the sense that you choose a metric on the base.
Oh, we just use this just the Euclidean metric as the base. Yeah.
The changes a bit for the discrete cases. So
Yeah,
there's
yeah.
some discrete examples where maybe the metric is having distance, taxi cab or something like that.
Mhm.